In our last lesson, we started learning about vectors in 2 dimensions. Here's an example, the same example from the last lesson. We've got a soccer player, and she undergoes a displacement from one position on the field to another. So suppose we're given this vector diagram, and we're asked to measure the magnitude and the direction of the displacement vector. Well, to make a measurement of the magnitude, that's the length of the arrow, you might be inclined to just get out a ruler and measure the length of it, but your ruler doesn't account for the scale of the diagram. So what we want to do instead is use the compass from your geometry set, or if you don't want to use that, you can just use a sheet of paper. So I've lined up one edge of the paper with the tail of the vector, and I'm going to use a pencil just to mark the tip of the vector. So now we've got the length of the vector recorded along the paper. What I'm going to do next is I'm going to hold the paper up against the axis. So I'm going to line up the bottom of the paper with the origin, and I can see that the top of the paper is at 25. So that tells me that the length of that arrow was 25, whatever the units of the diagram are. In this case, that's 25 meters. So let's record that off to the side. It doesn't matter whether you use the y-axis or the x-axis because they both have the same scale. For a vector diagram, we're graphing distance on both axes, and 5 meters in the x direction and 5 meters in the y direction have to be the same distance. So when you're drawing vector diagrams, always make sure to use the same scale for both axes. If you've got a diagram that uses different scales, that's stretching the diagram in one direction, so any measurements that you make are not going to be accurate. To measure the direction of the vector, remember we said in the last lesson that the direction parallel to the x-axis in the positive direction, we describe that direction as 0 degrees, and any other directions are measured as angles counterclockwise from 0. So using a protractor, we're going to position it so that the center of the protractor is on the tail of the vector, and the 0 degree mark is lined up with the direction that's parallel to the positive x-axis. And then we can read the direction of the vector just using our protractor. We can see here it's around 36 or 37 degrees. My computer can measure it really accurately, and it says 36.9 degrees. There's some other measurements we can make from the diagram as well. We can record the coordinates of the tail of the vector, which represents the initial position of the soccer player. So in this example, her x-coordinate is negative 10 meters, and her y-coordinate is positive 5 meters, so we can record that. Looking at the tip of the vector, the coordinates there tell us her final position. In this case, her final position has an x-coordinate of positive 10 and a y-coordinate of positive 20, so we can record that as well. Now we know from when we studied one-dimensional motion, there is a formula for displacement. Displacement is the final position minus the initial position. Well, we know the final and the initial position for our soccer player, so presumably we should be able to use the formula to subtract them. Now we introduced this formula when we were studying one-dimensional motion. So let's look at the motion one dimension at a time. Let's ignore the y motion here. Let's pretend that this is one-dimensional motion just along the x-axis. So suppose she's running along the x-axis. She's got an initial position of negative 10 and a final position of positive 10. We can illustrate that with an arrow, as you can see here on the diagram. And now we can use the formula, which says take her final position, which is positive 10, subtract her initial position, which is negative 10. If we subtract that, we get her displacement, which is positive 20. So that's telling me that this blue vector here is 20 meters long, and it's in the positive direction. So if this soccer player, if we're ignoring her side-to-side y motion, if we ignore her y motion, which is across the field, and only look at her x motion, which is straight down the field, she's moving 20 meters basically down the field. We call this the x component of the motion. So when we ignore the y motion and just look at the x motion, we call that the x component. And the symbol for that, we use the same symbol for displacement, which is delta d. We put a subscript x to indicate that we're looking just at the x part of the motion. Next, we can do the same thing for the y motion. So let's ignore her x motion. Let's pretend that she's moving just along the y-axis, starting with an initial position of 5 and going to a final position of 20. So we can illustrate that motion by an arrow from 5 to 20. We can use the formula again. If we subtract her final position of 20 minus her initial position of 5, that gives us a displacement of positive 15, which is telling us that that second blue vector that I just drew is in the positive y direction and it's 15 meters long. So that's called the y component of the motion. I've recorded the x and the y components of the motion separately. Sometimes you'll see them written together as an ordered pair. Just like with coordinates, we put the x component first and then the y component second. Now, before we go any farther, I'm going to move these blue vectors around a little bit. I'm going to take this x component, I'm going to position it so that it has the same initial position as the soccer player. Then I'm going to take the y component and I'm going to move it. I'm going to position it so it's got the same final position as the soccer player. And what you can see is that it now forms a right angle triangle. So if I draw the x component first and then I draw the y component in a tip to tail fashion, and by that I mean that the tail of the y component, I'm going to draw it starting from the tip of the x component. If I draw those two components in a tip to tail fashion, I get a right angle triangle formed with the displacement vector itself. Now we basically got two different ways of describing the vector here. So the first way we describe the vector here, we could say that it's got a magnitude of 25 meters, it's got a direction of positive 36.9 degrees. An alternate way of describing the vector is to say it's got an x component of positive 20 and a y component of positive 15. So if I ask the player to face in a direction of 36.9 degrees counterclockwise from the x direction, and then go 25 meters forward, I would be giving her instructions on how to get from her initial position to her final position. Alternatively, if I asked her to go 20 meters parallel to the x-axis, and then turn and go another 15 meters parallel to the y-axis, those instructions would basically get her to the same place. So we can think of the two different ways of describing the vectors as two different ways of getting from the initial to the final position. Now, the two methods don't follow the same path. The first method, the magnitude and the direction, we can think of it as an instruction on how to get from the initial to the final position following a straight line. The second method, using the x and the y component, takes a more indirect route. However, remember, when we're talking about displacement in physics, the route that we take doesn't really matter. All that matters is the initial and the final position. These two different ways of describing a vector are given names. The magnitude and direction, that's known as the polar form of the vector. The x and y components, that's known as the Cartesian form of the vector. The word Cartesian, that comes from the last name of René Descartes, a French philosopher and mathematician who came up with the idea of using coordinate systems. Now, do we really need both forms? Can't we just pick one form and not worry about the other one? Well, it turns out quite often when we're making measurements, the polar form is going to be more convenient. But when we have to do mathematical calculations, the Cartesian form is what we need. So we need to be able to work with both forms of the vector, and we need to be able to convert vectors between forms. In other words, if a vector is described in polar form, we have to be able to calculate what the Cartesian components are. And if a vector is described in Cartesian form, we should be able to calculate the magnitude and the direction. One way to do this would be to make an accurate graph of your vector, and then to convert it by making measurements. Unfortunately, this is very time consuming, and the results depend on how accurately you can draw the vector diagram and how accurately you can make measurements. So what we do next is we're going to use equations to convert vectors between polar and Cartesian form by calculating rather than having to rely on a vector diagram. Okay, now before we go to the next screen, I'm going to make a copy of this right angle triangle here, and I'm going to label it. So the red side, that's the hypotenuse of the triangle, that represents the magnitude, or the 25 meters, okay? The angle theta is the direction, that's 36.9 degrees. That's the direction between the x component, the x direction, and the vector itself. The x component is the adjacent side of the triangle, and the y component is the opposite side of the triangle. I'm hoping that you remember from math class that there are 4 equations that we can use that describe the relationships between the sides and angles in a right angle triangle. First of all, there's the Pythagoras formula, which is often written c squared equals a squared plus b squared. Then there are the 3 trig ratios, sine, cosine, and tangent. You may have heard the mnemonic SOHCAHTOA to help you remember which trig formula goes with which ratio of sides. Let's start with the sine ratio. So the SOH, so, means that sine theta is equal to the opposite side over the hypotenuse. So looking at our triangle here, the side that's opposite from the angle theta, that's going to be the y component. The hypotenuse, that's the side that's opposite from the right angle, or the longest side of the triangle. That's our magnitude, delta d. The cosine formula is very similar. Cosine is the adjacent side over the hypotenuse. So the only difference here is that instead of the opposite side, which is the y component, we're going to use the adjacent side, which is the x component. The tangent is equal to the opposite side over the adjacent side. So again, the opposite side is the y component, the adjacent side is the x component, so we can write tan theta is going to equal delta dy over delta dx. Finally, the Pythagoras formula says c squared equals a squared plus b squared. C refers to the hypotenuse, the longest side of the triangle, which is our magnitude. A and b refer to the 2 shorter sides, which are the x and the y components. So if I rewrite the formula using the sides as I've labeled them, the Pythagorean formula is going to look like this. Remember that in the original formula, the c is squared. So if I wanted to solve for c, I would need to remember to square root the formula. The first 2 formulas, which I've color-coded in red, those are the formulas that we're going to use when we want to convert a vector from Cartesian form into polar form. So if I'm given a vector in Cartesian form, such as a displacement of positive 20 for x and positive 15 for y, then I know all of the variables on the right side of the equation, of both equations, so I can solve for the variables on the left side. So let's get out a calculator. First, we'll use the Pythagorean formula. We're going to plug in for the x and the y components. We're going to plug in 20 and 15 into the Pythagoras formula, and that's going to give 25 for the magnitude, which is in fact the correct answer. To figure out the angle or the direction of the vector, we're going to use the tan formula. Now the equation reads tan theta equals the y component over the x component. In order to get theta, we need to get rid of that tangent operation. Hopefully you learned in math class that the inverse of the tangent operation is tan to the negative 1. So on your calculator, you can access tan to the negative 1 by pressing the second key and then the tan key. So if we rearrange the equation to isolate theta, we're going to calculate the inverse tangent of y over x. So typing that in on our calculator, the y component and the x component are still going to be 15 divided by 20, and the calculator will give us 36.9 degrees, rounded to 3 digits, which again, that's the correct answer. So by using the Pythagoras formula and the inverse tangent formula, we can always convert a vector from Cartesian form into polar form. Suppose we want to go the other way. Suppose we know the vector in polar form already, and we want to calculate the Cartesian components. Well, then we're going to use the blue color-coded equations, the sine and the cosine formula. If we look at the cosine formula, the unknown, the thing that we're trying to solve for, is the x component. So to isolate the x component, I'm going to have to multiply both sides by the denominator, which is delta d, the magnitude. And so the formula, when I rearrange it, is going to be the x component is equal to the magnitude times the cosine of theta. For the sine equation, we're going to do exactly the same thing. Since it's the y component that we're trying to solve for, we're going to have to multiply both sides by the magnitude, and so the y component is going to equal the magnitude multiplied by the sine of theta. So getting out my calculator again, I'm going to type in, for the magnitude, I'm going to type in 25, and for theta, I'm going to type in 36.9, and the calculator shows me that the x component, if I round it to 3 significant digits, is going to be 20.0, just as I expect. And then to calculate the y component, I'm going to do exactly the same thing, just one slight difference. I'm going to use sine instead of cosine, and again, I get the correct answer. If I round it to 3 significant digits, I get 15.0. Let's look at a couple of examples. Suppose you're told that a force vector is 100 newtons and has a direction of 140 degrees. So it doesn't matter what kind of force this is. It could be an applied force or a friction force. Doesn't really matter. Because it's a magnitude and a direction, this is the polar form of the vector. And you might be asked to convert this vector into Cartesian form. First of all, we could do it graphically. We can start by drawing a sketch of the vector to show how we would convert it graphically. So 140 degrees, that's greater than 90 but less than 180. So that's going to be in the second quadrant, somewhere between the positive y and the negative x-axis. The magnitude of the vector is 100 newtons, so when I'm choosing my scale, I'm going to have to make sure that I'll be able to draw a vector that's 100 newtons long. In this case, I've labeled the x-axis from 0 to negative 100, just to make sure I've got enough room to fit a 100 newton long vector. The vector is closer to the x-axis than it is to the y-axis, so I didn't go up quite as high on the y-axis. If I wanted to be especially careful, I could go up to 100, but I think we'll be fine just going up to 80. Let's draw the vector now. We would use our protractor to measure out a 140 degree angle. Remember, we always measure starting at 0, which is the positive x-axis. And then we would use our axis as a ruler here. So 100 newtons measured along the axis, I'd measure out that length, and I would draw my arrow having exactly that length. Once I've drawn the vector, I can now draw in the x and the y components. So remember that the x component starts from the tail of the vector, goes along the x-axis, and then the y component from there goes up to the tip of the vector, and they form a right-angled triangle. Having drawn the vector diagram, I can now estimate the x and the y components just by looking at the vector diagram. I should have mentioned that I put the tail of the vector at the origin. Remember that the origin is totally arbitrary. You can put it wherever you want. The tail of the vector is the most convenient place to locate it. Well, that being the case, the x component starts at 0 and goes to about 75. So that we can estimate the x component is about 75 newtons. The y component, it starts at 0 and it goes up to about 65. So we can estimate the y component to be about 65 newtons. If we want more accurate values, we're going to have to use the trig formulas. Now, the formulas that we have here, they're for displacement vectors, but it turns out that all vectors work the same way. The formulas for a right-angled triangle, it doesn't matter how we label the sides, the formulas still apply. So in each formula I'm going to change all these delta d's to f's. So the magnitude of the force is equal to the x component squared plus the y component squared, just like it is for displacement. In the second formula, I'm going to do the same thing. I'm going to change the delta d's to f's. Same thing in the third formula. Same thing in the fourth formula. You can use these trig formulas for any vector, regardless of whether it's force, velocity, displacement, or anything else. Now let's decide which ones we're going to use. The red formulas here, those are the ones we use to convert Cartesian to polar form. In this example, we've been given the polar form. We're trying to find the Cartesian form, so we're going to be using the blue formulas instead. To calculate the x component, according to the equation, we're going to take the magnitude, which is 100 newtons. We're going to multiply by the cosine of 140 degrees. So let's type that in on our calculator. And we get negative 76.6 rounded to 3 significant digits. So to calculate the x component, our equation says take the magnitude, which is 100, multiply by the cosine of the angle, which is 140. And if we do that, our calculator gives us negative 76.6. Our estimate, just by looking at the vector diagram, we thought it was somewhere around negative 75. So the calculated value is definitely going to be more accurate. Now we can do the same thing for the y component. According to the equation, we're going to take the magnitude, which is 100 newtons. We're going to multiply by the sine of 140 degrees, and that's going to give us 64.3. And again, that's pretty close to what we estimated the y component should be. If the numbers you're getting on your calculator are way different from what you estimated based on your vector diagram, most likely your calculator is in radian mode. Because we're doing trigonometric calculations like sine and cosine, double check that your calculator is in degree mode before doing any of these calculations. Now you might have noticed that the angle that we're using for the calculations, 140 degrees, this angle is actually outside the triangle. The angle that's inside the triangle is going to be 180 minus 140, or 40 degrees. So which angle should we use? Well, let's see what would happen if we had used the 40 degrees in the formula rather than the 140. Let's see what we would have gotten. So I'm going to type 100 cosine 40 degrees, and then I'm going to type 100 sine of 40 degrees, and you can see that the answers that I get are almost the same as the answers we had before. So 76.6 and 64.3, we get the same numbers. The only problem is that the negative sign is missing. If you use the interior angles, this 40 degrees, to do your calculations, you will always get a positive number. If you use the 140 degrees, the numbers will be the same, but you may get a positive or a negative answer. So it's better to use the 140 degrees, the angle measured the way we said in the last lesson, starting from 0. If we do it that way, then we'll not only get the correct number for our Cartesian components, we'll get the correct sign as well. All right, the final example is we're going to take a velocity vector. So let's suppose some object is moving with a velocity that has an x component of negative 18 and a y component of negative 35 in meters per second. So this is the reverse of the example we just did. In the previous example, we were given a vector in polar form and we had to convert it to Cartesian. This time we're given the vector in Cartesian form and we have to convert it to polar form. So again, we'll start with our diagram. We know that since the x and the y are both negative, we're going to need the third quadrant. Looking at the components, we want to make sure that the x-axis goes down to at least negative 18 and the y-axis goes down to at least negative 35. Again, using the origin for the tail of the vector, we'll first draw the negative 18, which is the x component, and then we'll draw the negative 35, which is the y component. So drawing those two vectors tip to tail, we can put the resultant vector, which represents the magnitude of the velocity from the origin to the tip of the last vector. So there is our right angle triangle. So this time, since we know the Cartesian components, we're trying to convert the vector to polar form. We're going to use the first two formulas that are in red here. And again, we're doing a velocity this time, so I'm just going to change the f's to v's in the formula, and everything else remains the same. So we'll take the first formula, we'll substitute the components in for vx and vy. Most of the time, I write the symbol for a vector with an arrow on top. We haven't done that in the Pythagoras formula, and the reason for that is because they're squared. So it doesn't really make any difference if the components are positive or negative. When we square the negative 18 or square the negative 35, it's going to be positive anyways. So we don't really need to worry about those negative signs when we're using the Pythagoras formula. So plugging the 18 and the 35 into Pythagoras formula, the calculator gives us 39.4, which would be the magnitude of our velocity, or that's the length of this red vector drawn in our diagram. If you do include the negative signs, you have to make sure to include brackets as well. If you leave out one or both of the negative signs, you'll either get the wrong answer or you'll get an error. And the reason that happens is because leaving out the brackets changes the order of operations. The calculator will do the squared first and then put the negative sign in, which is not what it's supposed to be doing. Then we'll go to the next formula, the inverse tangent formula, to calculate the direction of the vector. So we're going to type that in on our calculator. This time, the negative signs do matter. So we're going to type inverse tan of negative 35 over negative 18. We get 62.8 degrees for the answer. Now there is a problem with this answer. We can see from our diagram that the vector points into the third quadrant. So the direction has to be between 180 and 270 degrees. But the calculator gives us an answer of 62.8. The problem here is that the x and the y components are both negative. So when we use the inverse tan formula, negative divided by negative, the negative signs cancel. And so we get the same answer as if the components had both been positive. It turns out that there will always be two different directions that have the same tangent ratio. The calculator will always give us an answer between negative 90 and positive 90. So it will give us a direction either in the first or the fourth quadrant. When our vector points into the second or the third quadrant, the angle given by the calculator is this angle here, measured from the negative x-axis. So if that angle is 62.8, then the direction that we want is actually 62.8 plus 180. So on our calculators, we're going to add 180 to our answer, and we're going to get 242.8. So just keep in mind, whenever you've got a vector pointing into the second or the third quadrant, you have to add 180 to the angle, to the direction that the calculator gives you. You can tell if that's the case just by looking at your diagram. If it's pointing left, either up or down, then you have to add 180. You can also just look at the components. If the x component is negative, that means it's pointing to the left, which means you're going to have to add 180 degrees to get the correct direction.